off this morning's Hubble Fellows Symposium session. We're starting with Rongmon Bordoloi, who will be telling us about mapping the nuclear outflow of the Milky Way.
Thanks, Jen. The mic is on, right? Yes. Hello, everybody. This is my first time as a Hubble Fellow here. So I'm going to be talking a little bit about the project I have been doing here at Space Telescope in collaboration with Andy Fox and Jason Tomlinson and many other people. Essentially, we are trying to map the kinematics of the nuclear outflow of the Milky Way. When I say the Milky Way nuclear outflow, you obviously can guess you have to look towards the center of the Milky Way. And just to give a quick introduction, as you look towards the center of the Milky Way, one of the most prominent features that is going vertically out of the disk of the Milky Way are the Fermi bubbles. These Fermi bubbles were discovered, aptly named, as they were discovered in gamma ray emission by the Fermi telescope, are essentially giant plumes of hot plasma that is going vertically out of the disk of the Milky Way, and they are huge. They have a huge presence on the sky. They are covering all the way up to a galactic latitude of 50 degrees and around 15 degrees to 20 degrees in longitude. So these are huge structures in the sky of huge amount of hot plasma. They are not just seen in gamma ray, they are also seen in microwave, the so-called WMAP haze, which was initially discovered way back in 2004, and people were speculating that this could be a signature of dark matter. But over the years, we discovered that it's not dark matter, namely because you don't see it all over the sky, it's structured, and it's asymmetric along the bipolar direction. Plus, you just don't see it in microwave and gamma ray, you also see it in polarized radio emission, as seen by the SPAS survey. You also see it in hard and soft X-ray emission. So we know that there is a lot of hot gas out there, and it has possibly something to do with the central activity of our Milky Way galaxy. There are two working theories as to what might be the origin of such emission. One, which says that there is some sort of a very short nuclear outburst at the center of the Milky Way, and you have some sort of AGN activity or such, and that must have been very, very short and fast, and that's why you have the gamma ray emission, which is seen as inverse Compton scattering of electrons there. The second theory, which speculates that no, perhaps this is not due to some sort of AGN activity. Rather, it's some sort of secular process, some sort of slow star formation at the center of the Milky Way, which is slowly building up the structure that you see there. And that kind of model predicts that if that is the case, the gamma ray emission that is seen has to be some sort of hadronic collision with basically the cosmic rays with some heavy ions there. And that's a slow, gradual process which will take hundreds of megayears to build up. This is the theoretical knowledge we had and observational knowledge, all from emission line maps. However, we had zero knowledge about the kinematics of the gas there. So we set out to do a Hubble experiment where we want to actually trace the diffuse gas, cool and warm gas that might be entrained in the Fermi bubbles inside the hot plasma. We want to use UV spectroscopy to basically probe this gas as absorption line. So the idea is you find UV bright quasars that are lying behind the Fermi bubbles. You have sight lines, some of them which will pass through the Fermi bubble, and some of them which will pass not through the Fermi bubble, rather on the other side. And you should see some sort of differentiation in absorption line spectroscopy that will enable you to measure the kinematics, because with Hubble you have very high resolution spectroscopy. Plus, also say something about the kinematics of the outflowing gas from there. We just didn't settle for AGNs. We want to do a tomographic study. So secondly, we decided to set up some halo stars that will be sitting inside the bubble itself. So you can look for differential effects of a full sightline that probes through the whole of the Fermi bubble and something that probes half of the bubble. Then thirdly, we added some halo stars. These would be foreground control samples. You better not see anything there. If you see something there, obviously something is wrong with our thesis. So with this thesis, we set up to do the observation. And I'm going to focus on the first result that we presented here for the sightline PDS 456. This is actually the first sightline that was observed with HST COS spectroscopy for this program. PDS 456 is a very interesting sightline because it's sitting at the closest impact parameter to the galactic center. This is sitting in a region where you have excess gamma ray emission, which is seen by this residual red color in the background. Also where you have excess hard X-ray emission, seen in this overlaid X-ray plot. So what's up with the cool gas in train there? So when we looked at the HST spectra here, we got really excited. PDS 456 has a systemic, the Milky Way component would be at systemic zero velocity. Obviously, there's a huge component of Milky Way absorption there. That is understandable. But these wings here, the blue shifted component here and the red shifted component here, were telltale signature of a line of sight that might be passing through a biconical outflow. And because you're closer to the galaxy and there is a radial flow here, you'd have projected velocity components in this direction. You would expect to have blue shifted absorption if there was a gas cloud here and red shifted absorption if you have a gas cloud there. That's exactly what we observe. This is obviously for silicon-3 1206 line, which is tracing something like 10 per 4.5 Kelvin gas. So it's moderately cool gas. It's not just seen in this transition. When we went through the UV spectrum itself, we had tracers for many different phases. So we had tracers for carbon-2, aluminum-2, silicon-2, which were cooler gas at 10 per 4 Kelvin. And also for silicon-3, which is moderately warmer, carbon-4 and silicon-4, which were tracers for 10 to the power 5 Kelvin gas. So in all cases, you're seeing this kind of complex absorption structure. This clearly suggests that there is cool and warm gas present there, which are ionized. Then we went to the Green Bank telescope, got really deep 21 centimeter emission spectra for these sightlines. And for this one, we found no 21 centimeter emission lines there, which suggests that, not surprisingly, that the gas there is highly ionized. Remember, it's at a galactic latitude of 11 degrees. So it's very, very close to the center of the Milky Way. It's not surprising that the radiation from the center of the Milky Way, it will just ionize any gas that could be there. So we concluded from these results that this must be a signature of seeing the near and far side of an expanding biconical outflow. To quantify it better, we created a simple kinematical model, which is essentially, we fixed the opening angle of a bicon. We're just assuming there is a bipolar outflow there. We're fixing the opening angle of the bicone to be the opening angle of the X-ray bicone that we see before, which is around 55 degrees, 50 to 55 degrees. And then you're launching particles. You can say that, you can assume there could be different wind models. You can say it's the simplest case, first order. It's a constant velocity wind. So all the particles are going at constant velocity, first order of magnitude. The second one, you assume it's a momentum-driven wind. So you impart some momentum, so there is like 1,000, 1,200 kilometer per second momentum given at launch. Then you let it expand elastically. These are very, very simple models. And then you can predict for each line of sight, given at a latitude and longitude, what are the expected velocity range you should observe for these sight lines. So for example here, I'm just showing a distribution of velocities predicted for such a model. Note that these fancy velocity distributions color-coded here are actually tracing the rotation of the galaxy itself. Plus, you see that the velocity gradients here is sort of asymmetric. It's sort of going in a skewed direction. This is not a bug in the code. Rather, this is the near-field effect. Because you're inside the galaxy, so you're at a finite distance from the gas cloud. So actually, this will mean that your velocity fields will be tilted in this weird fashion. But since we can model it, we can actually predict what are the outflowing velocities here. And for these sight lines, we found that a momentum-driven wind, which is launched at around 1,000 kilometers per second, is pretty good at explaining this kind of velocity kinematics, which is great. But this is just, so we went ahead and said that we did discover the kinematics of the bipolar outflow of the Milky Way, and we claim that, we're seeing a wind which is being launched at around 1,000 kilometers per second. Awesome. But this is just one sight line. And as I said, we wanted to do a survey of the whole Fermi bubble. So the whole program has a huge number of sightlines, both in the north and south. The green points here are AGN sightlines. The red ones here are the halo stars that are sitting inside the bubble, and the orange ones here are the foreground stars. For the rest of the talk, I'm going to focus on the northern part of the Fermi bubble, namely because the southern sky is messy. You have the Magellanic Strings, which is passing through here. So when you want to interpret the absorption kinematics, you have to be very careful to identify which is belonging to which absorption system. Whereas the northern sky is much, much cleaner. So it makes my life easier to do a proper statistics up there first. Unfortunately, though, we have no foreground stars in the northern sky. So I did check with the southern halo stars that there is no foreground absorption there. No blue shifted or red shifted absorption there, just the Milky Way systemic component, which seems to be the case. So for the northern sky, I'm going to focus first on these 5 points which are sitting right in the middle of the Fermi bubble, unambiguously passing through the bubble. And I'm going to use those to actually trace out the radial profile of the outflowing gas as we go vertically outward or go out in impact parameter from the center of the Milky Way. So for the first object, I've shown you PDS 456, which is showing absorption, blue shifted absorption at around minus 235 kilometers per second, here at around 250 kilometers per second, which is, and you have 3 absorption components, which is quite complex. What happens if you go slightly upward? Lo and behold, you see that you still see blue and red shifted absorption. But notice this. Here the velocity is slightly less. So you're actually seeing deceleration as you're going upward. Plus, notice that the absorption for the red shifted component is much lower than here. Why is that? As you're going upward, your line of sight is actually tracing path lengths which are much, much higher scale length than this sight line here. So you're actually probing gas which is at a much higher impact parameter, which is very satisfying because if it were just random HVC floating around, there is no way you should see such radial profile of decreasing column density as well as kinematics. So as you go upward, for the halo star, this red point here, you'd expect that you better not see any redshifted absorption. That's exactly what we see. You see a very strong blue shifted absorption here. This is actually this spectrum, and these are HST cost spectrum, so you even have a much better resolution here. But the bottom line is you see a very nice absorption component in blue shifted absorption, but nothing in redshift. Then you can go vertically upward for the other 2 sight lines, and you see the same picture. Blue shifted absorption, and for the last sight line, which is at the latitude around 50 degrees, you see a wing of blue shifted absorption. And the fact that you don't see any red shifted absorption here suggests that you're actually tracing the edge of the bubble there. So you're actually tracing the interface region where you're basically just kissing the edge of the bubble as it's expanding outward. This allows you to construct, for the first time actually, for any outflowing gas, an observed velocity profile. As you're going up in latitude, you're actually plotting the velocities. Here I'm plotting the projected velocities as a function of line of sight velocity as blue points, and as a function of galactocentric, at the frame of reference of galactocentric rest as red points. You can see that at rest frame, it goes from around minus 280 kilometers per second, goes down to around 100 kilometers per second. So this is fantastic. Now for each sight line, we can actually invoke, well, just to show you how the sight lines stack up here. For each sight line, now you can invoke the biconical model again, like before. Thank you. You can shoot sight lines through it and predict what will be the actual observed velocity what will be the actual velocity profile, and because you are using the model, you can actually predict what is the radial distance of the absorbing gas from the center of the Milky Way. This allows you to create this plot where you're actually plotting the radial distance from the center of the Milky Way to each absorbing cloud. You can see that the PDS 456 is around 2 kiloparsecs, whereas as you're going upward, at the highest part of the absorbing cloud, it's at around almost 7 kiloparsecs. So you're actually constraining the entrained gas in the Milky Way's nuclear outflow. Having known this, you can also work out the inverse way. You know what wind model you're using. You can work out what is the kinematic age of the Fermi bubble. So you see, if you have to fill up the bubble with this kind of a wind model up to 7 kpc, you need at least 6 to 9 years, mega years, to launch the wind particles there. So as I said before, there were 2 competing scenarios. One was saying this, there was a short outburst for about a few mega years. The other one said there are a few hundreds of mega years of activity to form the bubble. From a completely independent method, from purely kinematics alone, we are saying that it must be a short event. I still cannot tell you if it is some sort of halo star activity, which O-star activity at the center of the Milky Way, which was because O-stars have a lifetime of around 9 mega years, or there was actually an AGN activity. But I can tell you, whatever it is, it's a short event. It cannot be sustained star formation for hundreds of mega years. We're completely ruling out that scenario here. Then we can go ahead and actually see that the incidence of absorption, what is the incidence of absorption inside and outside the bubble? Because we have shown that, I've already shown it that for the 5 sightlines, there is always high velocity absorption observed. What about the sightlines which are just outside the bubble? So initially we started with these sightlines, and as I probed outward, I got really excited because for 4 out of these 5 sightlines, 5 out of these 5 sightlines, I actually saw no blue shifted absorption, which is a telltale signature of the near side of the cone. For one, there is a positive high velocity component, which is not surprising because we do know that on the sky there's a lot of high velocity clouds, so you should expect something. But again, it's only 5 sightlines. So we wanted to improve the statistics. So we went ahead, looked at the literature, and basically took all the archival HST COS sightline in the northern sky in this part of the sky, basically, around the Fermi bubble. We ended up with a total sample of 47 sightlines. 5 of them, which I've already shown, are inside. 34 are outside. And 8 of them are sort of at the edge of the bubble. I call them the interface sightlines. And it's tricky because of the signal to noise of the gamma ray maps plus the angular beam size of the survey. You cannot really pinpoint this is exactly passing through, this is not passing through. So I can just tell you that these 8 sightlines are probably straddling the edge of the Fermi bubble, and they are probably tracing the kinematics of the wind which is terminating somewhere there. So obviously for these 8 sightlines, our simple model will not work. For the rest of the 5, it should work, and for the outside ones also, we can see if there is a higher or lower incidence of absorption. So when I did this test, we found out that the incidence of high velocity absorption outside is much, much smaller than inside. I mean, its current fraction is of around 20%. So clearly, there is an excess of higher velocity absorption inside the gamma ray axis area compared to the outside of it, immediate vicinity of the outside of it. So this is important. I'm going to go a little bit faster now and tell you that for one of these sightlines, we actually did observe a 21 centimeter emission line. So this is the second guy. For this guy, there was nothing. For the second guy, we did observe 21 centimeter emission. So this allows you to actually measure the H1 column density of the absorption species there, which in turn we can translate to a metallicity because with HST COS spectra, we had an O1 measurement. O1 is not depleted much onto dust, so it's a very, very good measurement of metallicity there. The metallicity we measured is slightly lower than what we would have expected. But again, this is not crazy. I looked up in literature for other outflows like MAD2. They also have subsolar metallicity in their outflowing gas. The bottom line is, since we know this metallicity, we can actually do some very back of the envelope but fun calculations about the mass flow rates in this outflowing gas. What I did was basically, we have a UV spectrum which covers 3 species of silicon, 2, 3, and 4 ionization states. So I can sum these silicon species up. That gives you a floor of the total silicon column density there. I can apply the metallicity there to do a metallicity correction to get the total H1 column density. Again, remember, this is not the total H1 column density. This is the floor of the H1 column density from the measured silicon column densities. Because I'm not taking any of the hot phase of the silicon or any other phases. So actually, the number I'll quote will increase as you account for the total mass. So it's a bare bone floor. And as I've shown before, that the covering fraction for such gas is pretty high inside the bubble. So for this calculation, I'm assuming it's 1. And for a mass-conserving outflow, you can write down the mass flow rate as this equation. And we know the opening angle to be around 55 degrees. You put in those numbers, and you get a mass loss rate of cool gas to be around 0.3 to 0.5 solar masses per year, just in the Fermi bubble region. What does it mean? Remember, the star formation rate of the Milky Way is 1 solar masses per year, roughly. So it's a mass loading factor of half. And probably, if I'm underestimating the total mass, it could be as high as an order of magnitude. So the total mass loss rate could be 3 to 5 solar masses per year. Again, we know the total age of the Fermi bubble. I can just compute, assuming uniform covering fraction, what is the total mass content. So you see that for a constant mass loss rate, you can work out that the total entrained cool gas mass could be as high as 5 to 10 to the 6 solar mass. It could be an order of magnitude higher, I don't know, but this is the floor. And this is fantastic because we do know that if you look in H1 21 centimeter emission towards the center of the Milky Way, there is actually a lack of 21 centimeter emitters at the center of the Milky Way. So perhaps are these gas being blown out and they are basically populating as entrained material the Fermi bubble? That's an open question, but that's something fun to think about. So I'm going to conclude with this. I'm running out of time. So here are the findings we found. We are actually detecting the outflowing gas in the Milky Way. We're computing an independent measure of the age of the Milky Way to be less than 10 megayears, and which is constraining one of the models of formation of the Fermi bubble itself. We're showing for the first time actually the outflowing velocity profile as a function of impact parameter from the center of the Milky Way. And we're computing that the mass loading factor for the wind there could be 0.5. Thank you.
Thanks, Rongmon, for a very nice talk. Questions? Peter.
What's the total kinetic energy?
So the total momentum flux is around 10 to the power 33, 34 ergs. I have to compute the energy. I haven't done it.
Are these HBCs the ones that are falling in?
So
The ones that were discovered.
these are not infalling. These are going outward. The reason you see them blue shifted is just because of they are going outward radially.
Are they the same basic thing as the ones that are falling?
They are not the same things. The reason I can say it safely is because of higher incidence inside than outside the bubble, plus the kinematic radial profile that falls off systematically, as you'd expect for radial flow.
I have a question. Can you put this in the context of outflows generally for spiral galaxies? I mean,
Right.
is this something that is just a little burp from the Milky Way, or is this something similar to the outflows
Right.
we see broadly?
So the numbers are surprisingly similar. So if you look for star-forming galaxies and the typical outflows they are driving, they would have mass loading factors of 0.1 to 1-ish, roughly, up to lower redshifts. As you go to higher redshift, they might go up to a mass loading factor of 10 or so. And the total momentum flux for starburst galaxies in the local universe is similar to what we are observing here. So it seems, in terms of energetics, perhaps we are seeing a similar scenario.
But this is all coming from the center, right?
This is all coming from the center.
So that's very suggestive of what's driving it, right? Whereas we don't know what's driving the outflows generally.
Yes. So again, that is different. For the typical starburst, it is the star formation that is driving. Whereas here, I'm agnostic. I really cannot tell you if it's the AGN or not. But it's suggestive of AGN, but some people might argue, what about the O stars? I cannot rule them out.
Okay. All right. Yes?
How well is this actually constrained to be at the center of the Milky Way? Like within, if it was a kiloparsec off, would reading this
It could be a kiloparsec off. That's absolutely correct, because it's not a perfect bicone. It could be that the actual launch radius is slightly lower than the center of the Milky Way. We don't really know that. We haven't constrained it. That's why I'm agnostic. What is the origin?
Okay, let's thank Rongmon again and move on. We had the